do is talk about this graph of this contour map. So let's see, we're in 13.8, part 2. So here's this contour map of a surface, and we have these points. We have these points marked on there. So first thing I want to do is what kind of on this surface, what kind of points could these A, B, C, and D be? So how about A? Yeah, could it be a max or a min, right? Because we could go downhill to get to A, or we could go uphill to get to A. How about B? Same thing. What about the other 2 points? Saddle points. They look like saddle points. C, comma, D. Is it possible? I've been going around and around with this one. Is it possible that those could be extreme points? If all of these, if you went downhill here, downhill here, downhill here, downhill there. I was thinking of like taking an X-shaped wire and then picking up like some pizza dough with it, and the dough would kind of droop off the edges, and the X shape would be all along there would be a maximum. So most likely I would say C and D are saddle points, but I think it's possible for a strange surface that they could be maxes or mins. Okay. And then what if we have a situation where we have f of x, y is a nice function. In an open disk about a point. And f sub xx at AB and f sub yy at AB have opposite signs. So what do we know? About f of AB? It's a saddle point, because in that case we have D, our discriminant, is f sub xx, f sub yy minus f sub xy squared. If these are opposite signs, that quantity is going to be negative, and we subtract something there, so we get less than 0. So we get f of AB is a saddle point. And this would tell us, essentially it's telling us that the slope is increasing in one direction and decreasing in another direction. So that's what happens at a saddle point. All right, we're good there. So let's go on to absolute extrema. The extreme value theorem. Tells us that f of xy attains an absolute max and min at some point in a closed bounded region. So for absolute extrema, we need to define a region also. So the difference, relative extrema, we're just interested in how is our function behaving compared to nearby points. For absolute extrema, we need a region. We're defining a region, and we say what's the largest that function takes on that region, and what's the smallest that value that takes on the region. And it would depend on the region. Just like a function of one variable, depending on the region, your absolute maximum minimum is going to change. And our absolute extrema we know that we can get an extreme value at critical points. So absolute extrema occur at critical points. Or on the boundary. So again, just like a function of single variable, when we're looking for absolute extrema, we look for critical points, and then we test the endpoints. For a function of two variables, our boundary can be some kind of curve, so we have to test for extreme values on the boundary. And depending on what the boundary is, that can be more or less complicated. All right, so to find these extreme values, to find absolute extrema on a closed bounded region, one, we find the value of f at critical points. And we only care about the critical points in the region. Two, we find the extreme values of f on the boundary. And finding the extreme values of f on the boundary goes back to what we've done in Calculus 1, where we're finding, and we will see that what we do on the boundary is we turn our function of two variables into a function of a single variable. We use the conditions on the boundary to eliminate one of the variables. So then we're finding the extreme values on the boundary. Now the interesting thing that happens is, for example, if part of the boundary is a line segment, we find the extreme values on the boundary, and we also have to then test the endpoints of the boundary. So there's another layer that we have to go through to find these extreme values. Our third one, that once we find these values, the largest value is our absolute maximum. And the smallest value is the absolute minimum. And this is on or in the region. So it's not necessarily the absolute maximum and absolute minimum of the function everywhere. We're just talking about a function in a particular region. So for example, yesterday we talked about a paraboloid, and we know that the minimum value of the paraboloid is at the vertex. But if we're talking about the paraboloid over this circle in the xy plane, then we project that up onto the surface of the paraboloid and we get this kind of oval shape. The absolute maximum and minimum of the surface above that circle is at the bottom of that oval and at the top of that oval. So it depends on what the region is, where your absolute maximum, absolute minimum are going to be. So this is not for the function everywhere. This is just in that region. So what I want to do is go through a couple of examples of some functions and some different regions to demonstrate the procedure. So we know how to do all of this stuff. We just have to put it all together. So step one is what we did last time. Find the values of fxy on the critical points. So we set the first partials equal to 0, find the critical points, and evaluate the function at those critical points. Part two is what we're adding today, finding the extreme value on the boundary. That usually takes a little more work, and it's not difficult. It's just depending on the boundary, it can be a fair amount of work. So let's take a look at an example. Questions before we go on? This is just like Calc 1, finding extreme values is the most kind of algebraically intense stuff that you do in calculus. Because when I learned calculus, I was disappointed because I thought, well, you do a couple of tricks, and then you're doing algebra. So you take a derivative, and then you're doing algebra. You do an integral, then you're doing algebra. So that was a little bit disappointing to me. But you have to embrace that because that's really what math is. You learn a new trick, and then you're back to doing algebra. All right, so we want to find the extreme value for all of these. Yes. Find the extreme values on the region. So the first one, f of xy is 2x minus y quantity squared. And our region, this is how one way that you'll be given a region. This is R for region. A colon reads such that. This one won't have curly brackets, the next one will. This one's just going to be defined verbally. This is R is the region in the xy plane. Between 2, 0, 0, 1, and 1, 2. So what's our region? A triangle. So let's draw a picture. Here's our, I'm not going to draw a picture of the function, I'm just going to draw a picture of our region because it's going to help us with what we're going to do. There's 2, 0. There's 1, 0. And there's 1, 2. Sorry, 0, 1. So our region is that triangle in the xy plane. So we have this surface, 2x minus y quantity squared, up here above this region. And we want to know the absolute maximum, absolute minimum value of the function in that region, above that region. All right, so I'm going to first find the critical points. So find the critical points in the region. F sub x, partial with respect to x, is 2 times 2x minus y times 2. And f sub y is 2 times 2x minus y times negative 1. And we want these to be 0. F sub x equals f sub y equals 0. Well, when are those two equal to 0? Aren't they equal to 0 when y equals 2x? So everywhere on the line y equals 2x, these are both 0 at the same time. So along a line like so, you get your first partials equal to 0. When y equals 2x, along y equals 2x, f of xy equals 0. So there's one candidate for an absolute extreme value. Is along the line y equals 2x, we get f of xy equals 0. So that's one of our candidates. All right, so now we need to examine the boundary. Well, in this case, what is our boundary? The perimeter triangle, 3 segments. So we have 3 segments, and we need to examine the value of f of xy, find the extreme values of f of xy along those segments. So, between, I'm going to do 0, 1, and 2, 0 first. Between 0, 1, and 2, 0, we can find the equation of that line. Y equals negative 1/2 x plus 1. That's the equation of that line. I can now substitute that into f of xy to get just a function of x. So along that boundary, f of xy equals 2x minus negative 1/2 x plus 1 squared. And I could simplify that. So that's 5/2 x minus 1 squared. And we need to find the extreme values along that segment. Well, how do we find the extreme values of our function along that segment? First derivative test, right? We take the derivative. F prime. So I'm being a little loose with the notation here, because here this is technically function just of x. I could write f of x comma negative 1/2 x plus 1. So we're substituting for y. And now we can just, I'm going to use the f prime. This technically is a function of 2 variables. We've just substituted for 1 to make it a 1 variable function. So I'm going to use f prime. So I'm being a little loose with the notation. F prime is 5 times 5/2 x minus 1. And f prime equals 0 when x equals 2/5. And I can, along the boundary, I can substitute this value of x into my simplified function. Because along the boundary, f of xy equals 5/2 x minus 1. So I'm going to say, and again I'm being, so I'm going to say f when x equals 2/5, f equals, when I substitute 2/5 in here, I get 0. So that's another candidate for the absolute extrema. So we have f equals 0 there. Yes.
Don't we have to test the endpoints for this line too?
Yes, we have to test the endpoints.
You would, Dylan. You
Classic
would.
Dylan.
No, actually, Shelby's that.
Yeah.
That was Shelby last time. That was on me.
So we have to test the endpoints of that segment.
Yeah, but Dylan, you're the same height.
F of 0, 1. Now, because that is on that segment, I can just plug in x equals 0 here onto the simplified function, into the simplified function. So f of 0, 1 is 1. So that's a candidate for now a maximum. And f of 2, 0, we substitute that. We can just substitute x equals 2 there because we're still on that boundary. F of 2, 0. 16. Ah. So that's our new candidate for absolute maximum. F of 2, 0.
Should we just do the last point and then become more points?
If we do the next, when we do the next boundary, then we test all the points.
All three of them, like right? Any
Yeah, you could test all 3 of the points. Yeah.
Was the candidate have you done the head part before you tested the endpoint? No, like after, yeah. Was it 0?
Yeah, at x equals 2/5.
And then for the first part, it was
Along
the line.
y equals 2x.
Alright.
So these are our candidates so far. We have f of 2, 0 is 16, and along y equals 2x, we get f of x y equals 0.
So can both endpoints be maximum relative maximums?
Yes.
And
Yeah.
just 16 is the absolute.
Right. Right.
So you have to retest endpoint.
It's a circle.
No.
Dylan,
So
Dylan,
once we tested this one, we don't have to test it again along the other boundary because we've already tested it. All right. So the second part here. Between between 0, 1 and 1, 2. We have to test there. Between 0, 1 and 1, 2, y equals x plus 1. So f of xy, when we substitute our simplified function, becomes 2x minus x plus 1, quantity squared, which is x minus 1 squared. And we need to find the extreme value of that function. So I'm going to say f prime is 2 times x minus 1. And this equals 0 when x equals 1. And I'm going to say, substitute that into my function here when x equals 1. F of xy equals f of xy equals 0. And we need to test the endpoints, right? We just need to test 1, 2. What's special about the point 1, 2?
It's along those lines.
It's along the first line, right? It's along y equals 2x. F of 1, 2 is 0.
You have to retest endpoints.
No. Yeah, we've already tested all three endpoints now, so we're good. This is along y equals 2x.
Would we have to say like test on what the test is at?
I'm sorry?
Do I have to say like along when I tested this endpoint along this line or something?
No, yeah, no. Yeah, I would see that you got them all. Yes. Yeah.
You also plug in the
So here, I just plug that into here. Because we're on that boundary. I can just plug, and that point's on the boundary, I can just plug it in there.
for the endpoints, can you just plug them into any of the functions? Like, can I do the boundary functions or the
Yeah. Yeah.
Okay. Whichever is easier.
Yeah. All right. And for this third one, I'm going to say etc. for the line y equals negative 2x plus 4 between 1, 2 and 2, 0. And we've already seen that f of 2, 0 is 16. We already know that. F of 1, 2, we already know is 0. We've already tested that one. And we get, between there, we get that the critical point along the boundary when x equals 1. And we've tested that one already. So our absolute maximum is at 2, 0, and we know that f of 2, 0 is 16. So the absolute maximum of that function is at 2, 0. And our absolute minimum for this function is along the line y equals 2x. And in that case, f of x comma 2x is 0. Let's take a look at that function and that region. So here's our region in the xy plane, that triangle. And there's our function above the triangle. There's our maximum up here at 16. And then if we look along the line y equals 2x there, we see it, the minimum is going to be right along the line there. I was very happy when I figured out how to do that shadow down there onto the xy plane.
The absolute minimum, what about an x at 2/5?
That was, so when x equals 2/5, that's along the line y equals 2x. Because there, if you plugged in,
So the y equals x plus
right.
1.
Mm-hmm.
Would that be? Oh yeah. Okay.
Yeah, so that's along the line y equals 2x.
Will we be given shapes that are not like a triangle or a square or something like that?
Circles are easy because you just have one boundary. But your boundary is y equals the square root of x squared minus 1 or something like that. So then you have to take the derivatives of that.
No.
So you could end up with just not as nice function.
Right, right, right. All right, let's look at one with a slightly not linear not all linear boundaries, just to see how it's a little bit different. But this kind of work that I just did on this one that's the type of work that you do with absolute extreme. So it's not difficult, but there's a lot of work.
I love how we only have 4 problems.
Right. Right.
There's 3.
47.
47.
And then you do 47 with a different boundary.
Yeah, it says 47.
You run one every
3 homework problems, they're all going to take you an hour.
F of xy,
2/3 of our whole
3x squared plus 2y squared minus 4y. And R is the region in the xy plane bounded by,
Always the region of the XY plane.
yes, y equals x squared and y equals 4.
So, Mr. Zuma, I
Mhm.
assume that we'll never have to deal with the variable equation for this.
No.
That would be terrible.
All right, so, and I just want to point out on the board over there, the region, the way I wrote the region there, that's, the way you would read that is the region is the set of x, y such that x squared plus y squared is less than or equal to 8. So that's inside a circle. So you'd find the critical points inside the circle, and your boundary would be the circle x squared plus y squared equals 8. All right, what is this boundary? It's like a U shape. So here's y equals x squared.
I can understand why you use it. Yeah. It does.
Flipping me a little scary.
Okay.
And here is y equals 4.
Sorry.
That's to me. I don't know what.
Bro, so the earth is flat.
So here we just have to examine two boundaries, and we just need the boundaries of the endpoints of the boundaries are just 2 points. So what is this point? Negative 2, 4, and this is 2, 4. So those are the endpoints of our boundaries, and we have a function up above this parabolic region, and we want to find the absolute extreme values of that function. So let's find our critical points. Our critical points, we get, this turns out nice, right? Because f sub x is 6x, f sub y is 6y. Sorry, no. 4y minus 4. I was being optimistic. 4y minus 4. So f sub x equals f sub y equals 0. When x equals 0 and y equals 1. F of 0, 1. Plug that in here and calculate. F of 0, 1 is negative 2. So that's one of our candidates for an extreme value. What is this? What is a surface?
Appears to be a elliptic paraboloid.
Yeah, it's going to be a paraboloid, shifted.
Come on, lady.
We have an x squared and a y squared, different coefficients. They're plus. So. All right, let's find examine the boundary. examine the boundary. So our first boundary on y equals 4. On y equals 4, f of xy, I'm going to substitute y equals 4 in here and simplify this. F of xy turns out to be 3x squared plus 16. And this is also between negative 2 less than or equal to x less than or equal to 2. So we're just going between these 2 points. F prime on the boundary is 6x. This equals 0 when x equals 0. And we already know what happens when x equals 0, right? F equals 16. All right, so that's our candidate for now for an absolute maximum. Now we'll look at the endpoints. F of negative 2, 4. I can substitute just negative 2 in here. And that's going to equal f of positive 2, 4. I have an x squared. Equals, when I substitute 2 in here, 28. So those are our maximums. So plus or minus 2, 4 is our new candidate for our absolute maximum. This one is not our absolute maximum. This is still our absolute minimum so far. And now we need to see if we have any extreme values on y equals x squared. On y equals x squared, we substitute that into our function. Substitute x squared for y. F of xy becomes 2x to the 4th minus x squared. And f prime is, we get 8x to the 3rd minus 2x. And I'm going to factor that. Equals 2x times 4x squared minus 1. So f prime equals 0 when x equals 0 or when x equals plus or minus 1/2. And f of 0, did we already try that? When x equals 0, we get 16. But along this boundary, along y equals x squared, f of 0 comma 0 squared is 0. Plug in 0 here. Well, that's not a minimum, absolute minimum, because we still have that negative 2. And when x equals plus or minus 1/2, f equals 1/4 times 1/2 minus 1, which is negative 1/8. So I'm substituting plus or minus 1/2 in here. It would be positive 1/8. So I'm going to say plus or minus 1/8, right? Positive 1/8 when x is positive 1/2. Still not small enough to be our absolute minimum. So our absolute maximum is f equals 28 at plus or minus 2 comma 4. And f equals negative 2 at 0, 1. Yes, absolute minimum. So let's take a look at this one. There's our parabolic region. Get it rotated correctly. There we go. In the xy plane. And there is our function. So here are our, there we go, get that bigger. There are our two absolute maximums on the region. And then our absolute minimum would be right in here.
Oh, it's a shoehorn. Thanks, Kyle.
So that's
What's a shoehorn?
yeah, it does look like a shoehorn. Kind of the section. It looks like I have a kind of a spork thing that has that's shaped like this.
Exactly.
This is the spoon, and there's a little serrated thing that's the spork, the fork.
Yeah.
Yeah.
Isn't that just a spoon?
Yeah.
It doesn't have the little extra thing.
What's that? Well, it doesn't have a handle. You hold on to it like that.
Whoa.
But it has little tines here, so you could use it as a fork.
But it doesn't.
Right, but that function does.
So then wouldn't that just be a spoon? Because all the spork is a spoon.
It's a shoehorn.
With tines
Tell
on
me
it.
how that sport
So
would
isn't
work.
this just a spoon then?
I don't see how it
I don't know, maybe couldn't you maybe you could turn it over and stab into something with these points. Yeah.
Where's the knife?
Stab into your finger whenever you
Well, this is infinitely thin, so it'd be really sharp.
Oh, right.
There you go, Connor.
It's infinitely sharp. Perfect.
Right, infinitely sharp. I guess you'd have to be really careful when you held on to this part. You'd have to pinch it. You couldn't grab it.
But it's not, it just has no thickness.
Right. Would you be able to grasp it?
I guess it's on a 2D straight.
In the limit, you could grasp it. Right. All right.
A trowel.
You know it's not going to be good when there's only time. You know it's going to be a mess.
Wait, so do we do 47 points?
Yes, in problem 47 gives you one boundary, and then you do the same problem, the same function, but with a different boundary.
Whoa.
So you can do the same function, but different boundary, and it turns into a different problem.
Wow.
All right, and if you need it,
Oh, yes.
solution to number 42 is on the video, Calc 3, 13.8, part 2. And this was, in the old book, this was problem 57. So I go through, and I think that's a function with a rectangular boundary. Yeah.
Is it 48 or 8?
Oh, sorry. 8. I was thinking 47, and then I was writing 8, so I kind of combined the two. All right, so this one I think is a function, and the boundary is a rectangle. So I have the solution to that on a video.